recently he completed his PhD, and he has worked on the potential benefits of recovering waste heat from suburban or commuter trains after by heat 2. This is a project, as some of you will probably remember, we had it in another conference, in another congress that we organized. The research by Henrique Lagoeiro was also sponsored by Transport for London, by the TfL, and the goal was to analyze the performance of the waste heat recovery system as a technology to supply heat for urban heating, and also to research on how the platform temperatures could affect the nearby stations in the London Underground. He has published a paper recently, and that's how we know of all this research. And the speech by Enrique is called Investigating the Heating and Cooling Benefits. I'm sorry, but we have lost all sound. Okay. Investigating the heating and cooling benefits of waste heat recovery from the London Underground for the heating. And I'll leave it there, and I'll give the floor to Enrique. Enrique, you have the floor. Thank you very much. Good afternoon to everyone. It is a huge pleasure to be here talking about my work.
And I apologize because my Spanish is a bit rusty, so I'm going to do my presentation in English. Let me just share my screen now with you. I think the function is disabled. So just to introduce myself, I'm Henrique Lagoeiro. I'm a research fellow at London South Bank University. And it's a pleasure to be here, as I've said. Thank you very much for the organizers for the invitation. I'm going to talk a little bit about the findings from my PhD project, which was done in collaboration with Transport for London, and looked at waste heat from the tube and the potential to integrate both heating and cooling benefits associated with the Bunhill 2 project. So just to start off with my agenda for today, I'll begin by giving you an overview of the heat decarbonization challenge in the UK and how waste heat can be crucial in overcoming this challenge. And then I'll move on to give you some context on the heat coming from the underground and how that led to the development of the Bunhill 2 project, so the Bunhill Waste Heat Recovery System. And I'll talk a little bit about the role of our research team and my project in the Bunhill system. So we did some investigations on heating and cooling aspects, and I'll share with you some of the modeling results that hopefully you find interesting. And I'll finish by concluding, talking a little bit about some of our further studies and also other projects in this area that hopefully you'll find interesting. So just to give you some context on heat decarbonization needs, it really relates to the change that we need to see if we want to meet our net zero targets by 2050. And for the UK in particular, heating accounts for nearly half of the energy consumption and around a third of carbon emissions. So this is a huge challenge that is many times overlooked. And at the moment, as many of you are probably aware, we have a huge opportunity to electrify, so change the way that we heat our buildings, move away from gas and use heat pumps, for example, to leverage the fact that the electricity grid has a very low carbon intensity. It has fallen by roughly 66% since 2013. So now it's a great moment really to explore electric heating sources. And heat pumps are key for that. And if they're coupled with district heating, we can really explore economies of scale and decarbonize cities with much better efficiency. And the UK government is quite aware of this opportunity and has put in place some policies that I think are interesting to mention. One of them is the Green Heat Network Fund, which aims to provide grant funding for projects that use low carbon heat sources. So they set up a methodology to calculate the carbon content of heat, and they will award projects that can deliver very low carbon content and great carbon savings. And there's also a zoning policy coming up soon, which will establish zones, as we saw earlier today in Denmark. I think they are trying to do something similar here in the UK, which is just to set up zones where it would be mandatory to connect to a district heating system. So the expectation by the government is that with these policies and with the current market and opportunities that we have, that heat networks can grow from meeting only 2% of the heat demand in the UK to meeting 20% of that demand. So this would require us to increase the overall demand met by 7 times, roughly. So you can see it's a huge challenge, and waste heat's key in that challenge, the key part of that puzzle, really, just so we can, explore and use heat pumps with much higher efficiencies. These are locally available sources, and by connecting to these sources, we can reduce our overall energy demand and also achieve higher levels of energy security. And just to talk a little bit more about waste heat and how it connects with district heating and cooling systems. So a little bit of what's been going on in the district heating and cooling community. This is a diagram that one of my colleagues has produced, which just shows the development of heat networks over time and how they started with the first generation all the way to the 5th. And the trend has always been towards lower operating temperatures, which provides us, again, with a very good opportunity to use heat pumps. And if we look at the 4th and the 5th generation, they're really about achieving carbon savings, great levels of electrification, and this really opens up the opportunity for waste heat to be used. This waste heat could be connected to central heat pumps, to decentralized heat pumps as well, and they can also leverage thermal storage technology, so we can respond to the grid. We can generate our heat when the carbon intensity of the grid is low, when the costs are low as well, and really achieve significant benefits. And just to mention some of the waste heat sources that could be interesting and that our research team has been investigating as well. I think we heard about data centers today, supermarkets as well. So these services, they require cooling, and where there is mechanical cooling, there is waste heat as well. So it's a big opportunity to decarbonize district heating and cooling. And also there are some higher grade heat sources, so with higher temperatures. Some examples are industrial plants, and another one that's a bit controversial at times, it's crematoria. So we can tap into these sources as well, and they might not even need a heat pump and are quite interesting. And there are also other sources that I think are more relevant to Madrid Subterra, which are, for example, electricity distribution systems, so cable tunnels, electricity transformers, and also sewage systems. Can be the sewers themselves, the pipe work, but also treatment plants as an example. So these are some of the sources that are quite interesting and that will be key in the future. And to talk now a little bit more about the London Underground, as we've heard today, underground railways are quite promising. And this graph here on the left-hand side really shows kind of like why. It compares temperature measurements from 2013 from the ventilation shaft where the Bun Hill system was installed, and compares that to ambient air. And you can see it's much more stable, higher temperatures as well. So it's a big opportunity. Previous works have estimated that nearly 500 gigawatt hour waste heat is released in the underground per year. And that heat comes mainly from the trains, particularly from braking. As you can see in this thermal image here, the tracks get quite warm as the trains are approaching stations to pick up passengers. So it's a big opportunity, but there's also some challenges and some problems associated with it, particularly since we're dealing with a very old system. Most of the heat gets absorbed by the tunnel walls, and they generally just go to the tunnels, and the soils get saturated, which ends up causing tunnel air temperatures to be quite high, particularly during the summer. And just to give you a context of how that has changed over time and what actually causes this, I think we heard earlier today about different construction techniques, and the underground really follows those. So we have mainly 2 different types of construction techniques that were used for old underground lines. So on the left-hand side here, we have the cut and cover technique, which was explained quite well earlier today. And this method was used for the Metropolitan, the Hammersmith City, the Circle, and the District lines. So these are subsurface lines, and they don't have the same issue as the deep tube lines have in terms of thermal comfort and heat generation. And on the right-hand side, we have an image that shows how the deep tube tunnels were built. So this technique used pneumatic tunneling. So it was a machine that cut through the soil, and they would provide tunnel linings with cast iron. And this technique was used for the Northern Line, the Waterloo and City, Central, Piccadilly, Bakerloo, all of these lines that were built in the late 1800s, in the early 1900s. And it's quite interesting to see how the system has developed over time. So I think these two posters here on the right-hand side really show how the underground was before. So Professor Potts, he mentioned how the soil temperature remains roughly stable. And in the very beginning of the underground, we would see that, you know, during summer, the underground would be a place where you could escape to avoid hot weather, but in winter as well, it would be warm and below, it would be pleasant, let's say. And it's really changed over time. And what we see now is a scenario where during the summer, some of these lines that were built a long time ago achieve very high temperatures. And this example really shows that. So we have the central line here in the middle, which is one of the old lines that I mentioned. And you can see temperatures going above 30 degrees. Same goes for the Bakerloo line and the northern as well. So it's a problem that's really we need to tackle. And at the same time, we have the potential for heat recovery. We have an issue with cooling. And just to mention some of the work that our research team has done and how we've come to work in this particular area. We've been working with London Underground now for about 20 years, since the early 2000s. And initially, the focus of the research team was really to provide sustainable cooling solutions for the underground. So the underground, it has installed some air handling units, which are commonly referred to as PAHU, so platform air handling units. And these can use different, types of technology to provide, chilled water. And in our case, we looked at, using seepage water. I think this is a big potential. I think the underground requires over 30 million liters of water to be removed from the network per day. So, and this is associated with seepage. So this could be used to cool stations, just groundwater as well, and also mains water. So from the water supply system could be used. And we've worked together with TfL to develop a prototype of a heat exchanger, so a platform air handling unit that was installed at Victoria Station. You can see here a photo of that air handling unit and a schematic really showing how the system works. So you take the heat, the cool water from a borehole nearby, and you put that through a heat exchanger that's located at the platform level. And these works, they helped really develop some of the platform air handling units that you can see today installed at different stations. So this is for Oxford Circus, and these are the platform air handling units that are installed today. And you can see them, I think, at Green Park Station as well. So it's some of the work that we started doing. And a little bit later than that, we collaborated with TfL on the MICA project, so Metropolitan Integrated Cooling and Heating. So this is where we started looking at the potential to integrate heating and cooling and using ventilation shafts. So it's kind of like the concept associated with the Bunhill system as well. And it's moving away from thermally activating the structure of the tunnel that we saw today, but using, particularly for these very old systems, ventilation shafts as a location for heat recovery and also cooling provision. And this led to the development of the Bunhill 2 project. So this is the first scheme to recover waste heat from the underground. And just so you know where it's located, this is a zoomed in view of central London on the underground map. And the Bunhill system is located between the stations of Angel and Old Street on the Northern Line. And this is what it used to look like before. So this was actually a disused station that was then turned into a ventilation shaft. And this is what it used to look like, as I've said, and now it actually looks like this, the energy center. The waste heat's being used from the underground, and how this project actually came to life relates to an extension of an existing heat network, which was located in the London Borough of Islington. So this was the Bunhill Heat Network, and its main source of heat was a large cogeneration plant. So a CHP engine was used to provide heat to nearby buildings. And Islington really wanted to expand this network, but also to move away from CHPs to provide cleaner forms of heat. And this is what led to this project. So as I've said, it's a ventilation shaft heat recovery system. And this schematic to the right-hand side shows roughly how it works. You have heat recovery coils, which are installed inside the head house that is above the ventilation shaft. And there's a reversible fan as well. And this is what allows the system to provide cooling as well as just to recover heat. And the coils are connected to a 1 megawatt heat pump. And the energy center also has 2 CHP units, a thermal store as well to provide flexibility. And it operates with flow temperatures of 75 degrees Celsius and return temperatures of 55. And the focus of our work has really been to really understand the merits of the heat recovery system. So the investigation that I'm going to show you now really focuses on that element. It doesn't really consider CHP engines, for example, as we were really interested in the novelty associated with this project. So it's just some more photos that you might find interesting of the system. So this on the left-hand side here shows the energy center without its cladding. So this on the right-hand side is the renovated ventilation shaft where the coils are installed. And these containers, they house the CHP units, and there's also a control room. And the heat pump is actually at ground level. You can't really see it from this photo. And on the middle here, we have the heat recovery coils. So this is what the coils look like. They are actually quite large coils. I think the face area is around 29 square meters. So it's a quite big heat exchanger. And here at the bottom, you see the reversible fan as well. And on the right-hand side, the 2-stage heat pump. So this is an ammonia heat pump as well, which was another big challenge for the project because ammonia in a very built-up place and area with a very tall building behind is a complication. So the heat pump is completely sealed and it sits within a container as well. And it has a filtration system, and also it's monitored for any leakage of ammonia. But ammonia was very interesting because it's a great refrigerant and it can lead to very high energy efficiencies for the plant. And just to talk a little bit more about our role in the project and our investigation, as I've said, the system can operate in 2 different ways. So extract mode and supply mode. Extract mode, it works by removing hot air from the underground tunnels and using that air as your heat source. And the system can also operate in supply. So you change the direction of the fan. And in that way, you can actually recover heat from ambient air. And after that air is cooled down, it can be supplied to the tunnels, therefore providing some cooling to nearby stations as well. So it's a bivalent system. And what we really wanted to do was to understand the merits and the benefits associated with both extract and supply, and also to be able to compare how the system would perform against typical technologies that are available for heating in the UK. And when we look at supply mode in particular, we also wanted to understand how the cooling that we can provide would impact the underground environment. So just to explain briefly some of the modeling work that we've done. So as part of my PhD, I developed a model using a tool called Engineering Equation Solver. And this model is able to calculate the efficiency of the waste heat recovery system based on temperature and humidity data, either for ambient air, if you're dealing with supply mode, or tunnel air, if you're dealing with extract. So one of the main elements, particularly when considering the cooling aspect, is condensation, particularly when we're using ambient air, which has quite a high moisture content. Condensation is a big issue. And what the model is able to do is to understand and estimate and predict if the coil surface would be fully dry, partially wet, or fully wet. And this allows us to really understand, how much of the cooling effect is actually sensible and it's causing a reduction in temperature, and how much is associated with just reducing the humidity of the air. The model also considers how much additional power would be required to run the reversible fan based on the pressure drop of the system. And we calculate energy and mass balances across, critical points of the system. So starting at the heat recovery heat exchanger. So we know how much heat's being recovered, and the energy balance also calculates the temperature of the fluid that's being used. And in this particular case, if we want to operate in supply for 6 months, some sort of antifreeze mixture would be necessary. And this, of course, was considered to calculate the pumping power associated with the system as well. And the other energy balance was at the evaporator. So since it's a very short loop, and in this case, any heat gain would be beneficial, we modeled the system assuming that the heat recovered would be equal to the heat absorbed at the evaporator. And then another energy balance is calculated to determine what would be the evaporating temperature for a heat pump, for this heat pump. And based on how much heat is required by the network, so we can simulate the performance for a full load condition where we deliver 1 megawatt of heat, or for a part load condition as well, when less heat is required. And based on the output and the energy balance on the cold side, so at the evaporator, we can also determine the COP of the system, so how much electricity is required to deliver a specific amount of heat. So this is really the backbone of our research and my PhD. And we use this model then to investigate system performance. So that, as I've said, we were interested in both heating and cooling, and we looked at energy, carbon, and cost aspects associated with the system. So the works really were based on the development of the model and also on some experimental research. So we collected data from the coils in the heat pump of the Bunhill system to validate our model. And then the model can tell us, how much heat the system is generating, the energy consumption while it generates that amount of heat, and also how much cooling it can provide to the underground tunnels. And just to go into a little bit more detail on the cooling element, the next step of the project was really to understand the impacts on the underground environment. So we were asking ourselves how we could really understand and quantify the benefit of cooling. So we've collaborated with Transport for London, so the transport authority here in London, to develop a model of the Underground Railway. So this was actually based on a bespoke tool that TfL owns. So they have a tool that consists of all of the information associated with the tunnels and the system itself. So this is a one-dimension finite difference model, and it's based on a tool called Subway Environment Simulation, which is also known as SES. So this contains information on the frequency of the trains, all the heat sources within the system, the passengers, and when they're loading, when they're boarding the trains, when they're leaving the trains as well. We've got information from the transport authority on that, and we can actually understand the system and model the system in terms of its thermal environment as well. And this is exactly what we've done. So basically, we've teamed up with them to use the waste heat recovery model that I developed to understand how it would impact temperatures at nearby stations. So as I've said, the model is able to calculate the temperature drop across the coils, considering condensation as well. So we know the temperature going in, we know the temperature drop as well, and knowing the flow rate and the temperature that's going into that particular ventilation shaft, we can then model the impact at nearby stations. And this is the second part of the project, which was really focusing on the cooling benefit. And just to share with you some of the results. So first, just to explain how TfL analyzes the thermal environment. So they do modeling of any cooling project, and this was quite similar. So they're just looking at how platform temperatures will develop in the future. So 2030 and 2050 are examples and are the years that we looked at in our particular investigation. And these results are for 2030. And the way that TfL analyzes the cooling projects and the thermal environment is based on peak platform temperatures. So the results that I'm showing to you here, they reflect what would be the average temperature for the hottest week of the particular year that we are looking at. and this is for peak hours, so from 4 to 7 p.m. So this is the average temperature for the hottest week. And what our model does effectively is really just to look at different scenarios, which is what we have here on the left-hand side, which consist of a combination of extract and supply mode. So scenario 1 is a do nothing condition. So this is when we're not supplying any cooling. And for the remaining scenarios, we actually add, 3 months of cooling each time. And as you can see, this impacts the COP of the system. So we're reducing the efficiency, which is something important to note, but we also get this significant cooling benefit as well. And we looked at 4 different stations, so Angel and Old Street, as I've said. So these are the stations that are adjacent to the ventilation shaft. And we're also looking at King's Cross and Moorgate, which are the 2 stations beyond the adjacent ones. And as you would expect, the temperature reduction increases if you increase your number of months that you operate in supply. And it was quite interesting to see how far it could get. Our results have shown that the delta T for Angel and Old Street could be of up to 7.2 Kelvin for peak hours. So this is a massive reduction in temperature. So it's quite interesting to see the potential that a system like this actually has. Of course, this is if the system was running for the whole year in supply, and this might not be interesting from the perspective of the heat network operator, who wants to of course, run the plant with the highest efficiency possible. But just to show you what this means, so by running the system, let's say for the whole year in supply, this would provide nearly 6 gigawatt hours of cooling per year. So reducing on average the temperatures at nearby stations by 6.8 Kelvin. And this would come at a cost of increasing the energy consumption by 21%. So there is a penalty, but there is a significant benefit as well. And I think this is just to highlight that for projects like these with different partners, it's very important to have things agreed from the very beginning so that we can understand all the benefits involved and really agree on how the system should be run to maximize outcomes. And the next bit of my research that I wanted to share with you is associated with just understanding how the waste heat recovery system compares to other technologies for heating. So we consider the outputs of the model to really analyze, how the system would operate against boilers, against air source heat pumps, which are it's like the business as usual. So gas boilers, the typical technology being used in the UK. And we also wanted to consider how the system compares against another low carbon solution, so air source heat pumps. And we developed a model of a heat network, which was very similar to the Bunhill network, but in this case, we're only considering, as I've said before, the waste heat recovery system. And we looked at, developed the model using a tool called Energy Pro, and looked at, what would be the actual carbon and cost benefits associated with the system when compared to the other counterfactuals that we were looking at. And just to share with you some of the results from this heat network model and explain how it fits together with the previous models that I've just mentioned. So in this case, Energy Pro is a tool that we use. It's actually a dispatch model. So it's not a physics-based model. You just provide inputs in terms of your heat demands and your energy market conditions, so the prices of electricity. And what the model does is it sets up what's the best operating schedule for your particular energy sources. So in this case, we've used the waste heat recovery model to estimate what would be the efficiency of the system. So the COSP values, so this is the coefficient of system performance. And those values were then used as an input to the heat network model. And as I said, we're comparing against gas boilers. So these figures just summarize the results here in the middle. On the left-hand side, we have the gas boilers. So these is the cost of gas, the emissions associated with gas. And on the right-hand side, we have the low carbon alternative, which would be air source heat pumps. And in the middle, I'm showing the waste heat recovery system on the left side, if it operated only in extract mode, so no cooling being provided, and if it operates for 6 months in supply, so with 6 months worth of cooling. So Energy Pro was used to model the flexibility of the system as well. So we're considering thermal energy storage and analyzing how the system would respond to time of use tariffs. So we're considering, hourly tariffs for electricity, so the system can really be optimized to operate when costs are low. And just to summarize some of the results, for the first one being in terms of the cost savings. So although, as I've said again, the cooling benefit relates to the railway operator, and the heating benefits are associated with the heat network. But if you combine them, the cost savings can go from 8% to 23% with cooling, which is quite significant. And the cost savings are low because in the UK, the disparity in price between gas and electricity is quite significant, is nearly of 3. So by incorporating cooling, we can make these systems more cost effective. And in terms of carbon savings, there are additional benefits as well. So it goes from 78% against gas boilers if we're only considering extract mode, and we can take that up to 83%. So as you can see, it's not a big increase as we observed for costs, and this is because the carbon savings are mainly associated with heating. So changing the way that you provide heat is already enough, changing to the waste heat recovery system is already enough to get almost 80% of carbon savings. And the last thing that I wanted just to highlight is another way of looking at the cooling benefit, and I think it really associates with the coefficient of system performance. So if you look at those warmer months, so from May to October, when the system would operate in supply, if it were operating only in extract, the COP would be of 3.4. But by combining heating and cooling operating in supply mode, the COP can increase to 5.4. So although you're reducing the heat pump efficiency, by combining the benefits of cooling and heating, your overall efficiency of the system can be much higher. And just to summarize some of the analysis that we've done in terms of the cost as well, we've looked at the scenarios that we modeled. We've modeled a bunch of scenarios really, and here I just wanted to highlight 2, which are 12 months in extract mode or a 50-50 operation. And what I just wanted to highlight is how waste heat is able to reduce the cost of decarbonization. So when you compare to air source heat pumps, and these are the costs on top of the savings that we get with gas boilers. But in terms of the levelized cost of heat, which is effectively the NPV of the project, divided by the total energy it would provide over its lifetime, what we can see is that the system is able to reduce the levelized cost of heat by 9% against air source heat pumps. And when we look at carbon abatement costs, so these are, once again, we look at the NPV and divide it by the total carbon savings that the system would deliver against the reference case. And as I've said, the reference case in this case is gas boilers. And we could reduce the cost per ton of CO2 that you avoid by 18% against air source heat pumps. So it's a significant benefit that can be achieved with waste heat recovery. And when we look at the whole of London, for example, TfL has shortlisted 55 different ventilation shafts that are spread across the city that could be interesting from the perspective of waste heat recovery. And if we were to develop similar systems to the Bunhill system for each of these shafts, we could achieve carbon savings of up to 53 kilotons of CO2 equivalent per year against gas boilers. And this would come at a cost that is nearly 6 million euros lower than what would cost to meet that same heat demand with air source heat pumps. And just to provide some conclusions and mention some of our next steps in this research. So we've looked at waste heat, we've evaluated all the benefits, heating and cooling. There's also flexibility and air pollution that we included in our analysis, but I'd just like to mention them here as additional benefits as well. And we developed this novel approach that combines different models really to assess the benefits that we can achieve. And what we found is that waste heat can reduce the costs of decarbonizing as opposed to other low carbon technologies. And this is really associated with the high efficiency that we get by recovering waste heat, and also by the fact that by using these energy centers, these centralized energy centers, we can have much higher levels of flexibility by incorporating greater volumes of thermal storage. And in terms of the cooling aspects, very important to highlight as well, as it can improve both the levelized cost of heat and carbon abatement costs, and it can also alleviate station temperatures quite significantly. And this is a key thing if you think that This year in London during the summer, temperatures above 40 degrees Celsius were recorded. So cooling will gain importance in the future, and it's very key that we have a system that is able to operate bivalently. But this comes at a cost of reducing system efficiency, so a balance between all stakeholders and between the heating and cooling benefit is really needed. Another thing that I want to highlight is associated with policy. Electrification leads to higher costs. That's associated with the way the energy market works in the UK. As I've mentioned before, gas is nearly 3 times cheaper than electricity. So we really need to find ways of leveling the playing field between gas and electricity. And one way is really to align levies and taxes in the UK. Renewable energy projects, particularly for electricity generation, are funded through electricity bills. And a good way of really balancing this competition would be to align these levies between gas and electricity. And also, if you think about the recent energy crisis associated with Russian invasion of Ukraine, the prices of gas have increased more than the prices of electricity. So the gap is in some way reducing, but there's still lots to be done, really, to make sure that, you know, we get the benefit of the cheap electricity generation that is provided with renewables. Flexibility and air pollution, something that I touched upon quite briefly, but overall we looked at flexibility by considering, and also not only flexibility, but energy efficiency, by considering how the waste heat recovery system would impact the electricity grid. So the Energy Pro provides results in terms of the peak electricity consumption for the system. And for waste heat, it was 44% lower than for air source heat pumps. And I think earlier today, Marina talked about impacts on the grid and the importance of considering these elements of waste heat as well. And I think this is a huge benefit, because by reducing our peak demand, we can reduce costs associated with reinforcing the network, for example. And by bringing all these benefits together, we can really unlock the potential for waste heat. And just to mention some of the next steps in our study, we want to monitor the performance of the Bunhill system closely. So this work was done when the system was being commissioned. So we really looked at the potential rather than the performance over a heating season, for example. But we did validate our models with data from the Bunhill system, and we hope to be able to monitor the performance over the long term, understand its impacts, measure the impacts at nearby stations as well, just to see that the model benefits are similar to the actual impacts that are being observed. And we also want to look at alternative designs, you know, lower distribution temperatures on the network, how that would impact the benefit of the system, and also compare it to other technologies, not only air source heat pumps, but other, you know, low carbon heating technologies, and also other waste heat sources. And just to briefly mention something, everyone, that I think, if you're interested in our work, if you found this presentation interesting, I encourage you to visit websites of some of our projects. I'd like to mention 2 here: Green Skies and LotNet. So Green Skies is a project that is being carried out with the London Borough of Islington. And it's about a 5th generation heat network, so very low distribution temperatures. And the idea is really to be able to tap into all these different waste heat sources. So it includes waste heat from the London Underground, and includes waste heat from a data center. And I think from the perspective of Madrid Subterra, it also uses the London Aquifer as a way of balancing the system, which you might find, you know, quite interesting. So please visit the website, have a look. I think this really relates to the need to integrate things. The project also involves mobility. So we're really looking at these energy centers as energy hubs, where you can have heat pumps that respond to the grid, where you can have PV installed, and where you can have charging infrastructure for electric vehicles as well. So there's lots of potential. And in terms of the LotNet project, it's really a more academic project. It's between London South Bank University and other 3 UK universities. And we're looking at low temperature heat recovery, distribution, and network technologies. So lots of the work that we do on a more academic perspective on waste heat is available in the website. So please have a look, and feel free to reach out. And I'd just like to finish by thanking you. I'm sorry if I overran a bit, but yeah, it's really great to be here, and thank you very much for listening.